At the start of 2025, deep beneath the ground at CERN, the legendary machine known as the Large Hadron Collider roared back to life once again. Inside that massive 17-mile-long circular tunnel, the air vibrated with energy as protons were hurled to speeds just shy of light itself. This is the boundary between physics and philosophy, where humanity continues its relentless quest to uncover what reality truly is. Hey there, everyone! Today, we're diving into a series of strange and puzzling phenomena that completely shook the minds of scientists. So if you're into these kind of deep and mysterious topics, make sure to hit that subscribe button. Just a heads up, this isn't a scientific paper. It's a storytelling journey that mixes explanations with metaphors and bold theories to help make it all easier to understand. Welcome to our channel. Alright, let's get started. Inside CERN. Scientists working at CERN are pretty used to seeing experimental results that don't always line up with theoretical predictions. Nature, after all, has a way of keeping people on their toes. But this time, things went far beyond the usual, "oh, that's interesting" reaction, and straight into "this is absolutely impossible because it simply cannot happen" territory. In the middle of billions of ordinary particle collisions, something strange suddenly showed up, a bizarre signal out of nowhere. At first, the researchers assumed it was just a glitch, some noise, or maybe a hiccup in the detector system. But the more they analyzed it, the more they realized something undeniable. This was no malfunction. What they found didn't just clash with the world that physicists had mapped out in their equations. It was something that completely broke away from it. This time, the universe wasn't just trying to surprise us, it came at us full force, ready to overwhelm. And honestly, it did exactly that. The Large Hadron Collider is the most ambitious scientific machine ever built by humankind. Its tunnel reaches as deep as 575 feet underground, stretches across the border between Switzerland and France, and at its core, thousands of scientists from all over the world work side by side. This is the place where the discovery of the Higgs boson once rewrote the very textbooks of physics. But CERN's ambitions didn't stop there. The year 2025 marked a turning point. It was the final year of full operation before the collider was scheduled to shut down for major upgrades. And during that year, the scientific teams pushed their detectors, ATLAS and CMS, to their absolute limits, hunting for things beyond the known boundaries of the standard model. To aid in that mission, a new algorithm was introduced into the accelerator, the anomaly trigger. It was designed to ignore trillions of ordinary events and focus only on the extremely rare signals, those oddities that might look like errors but could actually be signs of brand new physics. And in practice, that method is already helping scientists search for hidden particles that don't leave any direct trace in the detectors. Instead, these elusive particles show up through weird energy patterns or strange breaks in symmetry. Throughout history, mismatches like these have led to huge breakthroughs, from neutrinos all the way to the discovery of the Higgs boson. That's why at CERN, no strange noise or statistical blip is ever brushed off as just an error. It might be the key that unlocks the door to an entirely new dimension. And if the leaked information turns out to be true, then at the very beginning of 2025, one of those doors may have finally, just barely, cracked open. Twin particles, the reflected trajectory. At first, everything looked perfectly normal, just like any other day. Millions of collisions were taking place, and billions of lines of data streamed into the computers, while the servers roared away doing their usual processing. But right in the middle of that routine, something incredibly strange began to appear. The signal didn't match any existing theoretical models, and it fit with none of the known symmetries. It was as if the particle had split into two separate entities the very moment it came into existence. Two objects, nearly identical in nature, suddenly popped up at the exact same spot in space, but they moved in totally different ways. It almost felt like one of them existed in a slightly shifted phase of reality, just a hair off from our own. At first, the physicists assumed this had to be a hardware problem. They double-checked the experiment, recalibrated everything, and verified all the settings, but it all came back perfectly normal. Yet this phantom signal kept showing up again and again, and always under one specific condition: only when the collision energy fell within a very narrow band. Unfortunately, the exact numbers for that energy range haven't been released to the public. However, we do know that during the 2025 run, the collider operated at 13.6 tera-electron volts. So, what exactly does 13.6 tera-electron volts mean? It translates to 2.18 times 10 to the minus 6th power joules, or just 1/2 of a joule. You're probably thinking, wait, that's barely any energy at all. And you'd be right. It's only about as much energy as a mosquito needs to lift off the ground. But that tiny amount of energy is packed into a space smaller than a femtometer. That's 1/1,000,000th of a millimeter. That's what creates such an extreme and violent environment. To make that easier to grasp, let's look at an example. Even a regular flashlight gives off about 100 joules of energy in just a few minutes. But that same 100 joules, if focused into a single arrow fired from an English longbow, would be enough to punch clean through armor 650 feet away. So what really matters isn't the total amount of energy, but how incredibly concentrated it is. When energy reaches these kinds of insane densities, it gives us a rare opportunity to pierce the fabric of reality itself and take a glimpse beyond it. And what appeared beyond that veil was something deeply unsettling. A particle that split itself in two. The scientists gave this bizarre phenomenon a name: the reflected trajectory. None of the known fundamental forces are capable of producing anything even remotely like it. Some theoretical physicists have cautiously proposed a bold idea. What if we've just encountered a particle that's entangled with its own mirror image? Maybe we've witnessed two parallel branches of the same quantum system overlapping for the very first time. And right after that, something even more disturbing was recorded. A faint pulse would occasionally pass between the particle and its twin, as if they were exchanging information instantaneously, completely ignoring the usual laws of locality. It genuinely felt as if these particles were communicating with each other somehow. CERN's official statement was brief and extremely cautious. But behind the scenes, more and more scientists are whispering, if this isn't a malfunction, then our model of elementary particles isn't just incomplete. It might be completely wrong at its very foundation. And what lies ahead for us may not be a simple tweak to a few equations, but a full-scale reboot of physics as we know it. Echoes from the future. But the truly bizarre part was still waiting just ahead. As physicists were layering and analyzing thousands upon thousands of event data sets, they stumbled upon something that made their blood run cold. In some of those records, the path of a particle had been logged, unbelievably, before the particle had even appeared. On the graph, a pair of impulses showed up. The first one was faint, almost hesitant, while the second was sharp and unmistakably clear. But that faint signal had appeared nanoseconds before the particle itself was born. It was like a mirror showing us something that hadn't even happened yet. The scientists couldn't believe it. Could this be a timing malfunction? Maybe the atomic clocks are off, they wondered. But after thorough testing, it turned out the instruments were working flawlessly. Even in repeated trials, the exact same phenomenon kept showing up. That's when a new theory quietly emerged. What if we are actually witnessing a kind of resonance between parallel quantum states of the universe? And not in the sci-fi sense of some distant alternate dimension, but as another valid solution to the same wave function. A parallel version of reality brushing up against ours for just the briefest instant. This reflected trace didn't carry a full energy signature. It appeared dim, almost ghost-like, as if it had come from another world that existed at a completely different vacuum energy level. Some researchers cautiously described it as a translucent mirror between two worlds that, just for a moment, had become thinner than usual. The particle itself hadn't crossed over through the mirror, only the information about that particle from another reality had slipped through. It was as if an alternate solution to the universe had barely touched our reality for a split second, leaving behind the faintest whisper on the detector. And if that's true, then CERN's experiments might not just be influencing our universe. they could be reaching across the overlapping structure of existence itself, affecting neighboring universes as well. The collapse of the Quark model. Quarks. They've long been thought of as the most solid bricks making up our universe. Protons and neutrons are built from quarks, and everything around us, all matter, ultimately comes from them. For decades, the behavior of quarks has been described with incredible accuracy by the Standard Model of particle physics. To physicists, quarks were like bricks to a master builder, reliable, predictable, and steadfast. But in early 2025, those very same quarks became the source of a brand new shockwave. During a set of collision experiments under specific conditions, the well-behaved B quark, also known as the bottom quark, started acting like it was following a completely different set of rules. Its decay pattern veered off course, bypassing all known probabilities and standard pathways. And, even more unsettling, right between the start and end of that decay, a brief intermediate state appeared, something that should not exist. These flashes showed up and vanished in an instant, leaving no trace of the usual decay products behind. It looked as if the particle had fallen into some kind of space governed by unknown laws, a hidden corridor we never knew existed. In string theory, phenomena like this are described as resonances of compactified dimensions, but until now, that idea had only existed in mathematics. Now those signs suddenly showed up in a real-world experiment. Quarks no longer looked like the basic building blocks of everything. Instead, they appeared more like tiny holographic flickers briefly surfacing from a deeper structure beneath our space. Could this be what quarks truly are? Not actual solid components of matter, but just holographic projections from a more fundamental layer beyond the boundaries of our space. If this turns out to be true, we'll have to admit we still don't know what matter is really made of. What we've believed to be the foundation all along may actually be nothing more than the outermost surface of a reality that's far more complex and deeply layered than we ever imagined. Energy with no source. The strange anomalies didn't stop with the twin particles. During one highly controlled collision session, where input energy was tightly regulated, detectors recorded something startling. The total energy of the particles that were produced was too high. The accelerator hadn't supplied any extra energy, not to the electrons, not to the electromagnets, and all calibrations were perfectly aligned, with control data showing no abnormalities whatsoever. Yet this energy mismatch only occurred under one very specific set of conditions. It happened when three factors came together: a narrow mass range, a fixed trigger setup using real-time filters, and a repeating pattern in the collision timestamps within the beam. The first explanation scientists came up with was that the energy had been borrowed from the vacuum. According to quantum field theory, vacuum fluctuations can temporarily cause tiny bursts of energy to appear and vanish. But this effect didn't behave like random noise. It acted more like a brief, controlled pulse that only occurred when every experimental condition was perfectly aligned. It was as if the entire system had been struck by a sharp jolt of energy, delivered in perfect rhythm. And that's where this bold new hypothesis came from. The idea is that the experiment may have momentarily pierced the boundary between our space and an external energy backdrop, possibly that theoretical zero baseline from which the universe itself is thought to have emerged. If that boundary is actually permeable, then our understanding of energy conservation may not be as airtight as we once believed. This universe might not be a sealed-off chamber after all. It could be more like a thin membrane, occasionally leaking something alien into our reality. And that leads us to one very troubling question. If energy can flow in from seemingly nowhere under certain conditions, then could it possibly leak out under different ones? Of course, this isn't a final conclusion, it's more of a warning sign. But sometimes it's these warnings that end up rewriting the textbooks. They make us re-examine our constants, re-evaluate our symmetries, and force us to ask new questions. Maybe we are standing at the edge of another layer of reality that's been hidden in plain sight all along. Time loops. The next strange phenomenon didn't come from space, it came from time itself. A reanalysis of the system logs revealed that several recorded events had slipped out of strict chronological order. Sometimes they appeared nanoseconds earlier than what calculations should allow, and occasionally they showed up just a tick late, as if someone had nudged the timestamp slightly out of sync. It didn't look like random noise. In fact, the timing shifts seemed to form a pattern, showing up only during specific parameter settings and within precise windows of time inside the accelerator. The system was synchronized with atomic clocks, and everything from calibrations and beam optics to the version of the trigger was fully aligned. And yet, in some data streams, it looked as though the data had begun looping in on itself. A faint signal would show up just before the event, and a brief echo would appear exactly 1 nanosecond after. When those signals are layered together, they created a closed loop in the pattern of time itself, almost like causality had snapped for a brief moment. The most disturbing part was this: a single particle showed up in multiple distinct states, all within the same reconstruction timestamp. Normally, logic tells us that causes come first and effects follow. But in this case, the effect seemed to arrive nanoseconds before its cause, as if it were catching up to the trigger that created it. Theoretical physicists have avoided making any hasty conclusions. According to textbooks on general relativity, there's a mathematical possibility for something called a closed time-like curve to exist under extreme conditions, a loop in time, but that's always been treated as a purely theoretical abstraction. What we're seeing here isn't some Hollywood-style time loop, but a localized breakdown of cause and effect at the quantum scale. Under normal circumstances, this kind of fluctuation would be averaged out and disappear without a trace. But this time, it was observed repeatedly, and it was directly tied to specific experimental conditions. So what does all of this mean? At the very least, it suggests that when we peer too deeply, the structure of time itself may begin to bend. In the most extreme interpretation, causality may not be an absolute law, but something that softly wavers in the delicate, shimmering world of quantum mechanics. And if that's true, then what we call the arrow of time might not be a rigid iron rail, but a stretched string that occasionally hums with the quiet resonance of something far stranger. Could this be interference from outside? In trying to make sense of all these anomalies, the twin particles, the faint precursors, the energy surplus, and the local breakdowns of causality, 2 working hypotheses have started to emerge. The first is the idea of external interference from a deeper background. If our universe is just a bubble floating inside a much larger field, something we might call the meta-vacuum, then under certain extreme experimental conditions, the membrane of our universe might become slightly permeable. That could allow directional pulses of energy, faint echoes of entirely different physical laws, and tiny time shifts to seep through. In other words, information might be slipping in through cracks that shouldn't even exist. What backs up this hypothesis is the fact that these effects have been observed repeatedly, under the exact same timing and filtering conditions. It doesn't look like chaos, it looks like resonance. The second hypothesis is that we're seeing the mirror-like response of the universe itself. And this isn't some simple alternative. It's the radical idea that there is no outside at all. By pushing this system to its extreme, we may have triggered a response from the universe, not just altering the results of our measurements, but reshaping the entire context of the events themselves. If that's true, then those faint traces weren't messages from another world, but the informational shadows of our own quantum states, overlapping in delicate gaps between moments. In that case, observation isn't something done from the outside. It's an active knot, woven right into the heart of the phenomenon itself. Both of these hypotheses demand rigorous testing. That's why the research team is choosing the one path that might be boring, but is also the only honest one. They're doing cross-checks between detector channels, using blind samples, adjusting trigger settings, rebuilding data from different angles, and comparing it all to periods where no anomalies appeared. And if this signal manages to survive that long conveyor belt of skepticism, then it won't just be an interesting fluctuation. It will mean we've opened a brand new chapter in the story of physics. When physics becomes philosophy. Everything we've explored so far, the anomalies, the strange signals, the ripples in causality, none of it has been officially confirmed as of August 2025. What we've shared are the possible scenarios and interpretations based on the data we have so far. The original goal of the experiment was actually pretty straightforward. Accelerate, smash, measure. That was supposed to be it. But the data has led us somewhere far stranger, into a realm where even familiar words like particle, time, energy, and observation start to lose their simple meaning. Maybe quarks aren't foundational bricks at all, but holographic flickers rising from some hidden underlying structure. Maybe energy is something that sometimes seeps in from beyond the edge, a pulse from outside. Or maybe it only exists because we're asking the system a question. And maybe the arrow of time isn't a straight line, but a tensioned string, lightly humming with the overtones of fractured causality. Should we be afraid of this? Science has always grown strongest in the places where the old frameworks break down. Every so-called impossibility is an invitation to recalculate the universe from scratch, to check our constants, rewrite our algorithms, and knock our own egos down a peg. Because CERN hasn't just accelerated protons, it's accelerated our understanding of what reality even means. And if, at this very moment, the universe is whispering something to us in a voice so faint we can barely hear it, then we have a responsibility to listen with everything we've got. What we need now isn't flashy headlines. It's patience, craftsmanship, more data, stricter tests, and a more honest kind of skepticism. Because stepping into the unknown is terrifying, but that first step is sometimes what opens up an entirely new sky. If you found this video fascinating, give it a like and share it on your favorite social media. Thanks so much for watching. We'll see you next time. Take care.